Hello everyone, welcome to the numerical methods class. We are going to talk about chapter 7 and it is about the roots of polynomials, especially for the complex roots. We are going to show some methods, numerical methods, how we can determine the complex roots of polynomials. In chapter 7, we are going to talk about the polynomials which are in this form. As you can see here, we have some constants multiplied by a variable x, and that variable has an nth order. So this nth order determines whether we have real or complex roots, and usually an nth order equation has an n number of real or complex roots. And the n is odd, like 1, 3, 5, then there is at least one real root. Then if we have a real root, we can use the methods that we learned in chapter 5 and chapter 6. However, if we have complex roots, then they are in conjugate pairs, meaning that we will have, for example, lambda plus mu I and lambda minus mu I. This is called conjugate pairs, and the I is, as you know, this is square root minus 1. And these cannot be solved by the methods in chapter 5 and chapter 6, rather they can be solved by the methods in chapter 7. So we are in chapter 7, and the methods that we are going to use for finding these complex roots are at chapter 7 for Müller's method and chapter 7.5 Bayer-Stokes method. And there are of course other methods as well, like Jenkins-Straub method, Laguerre's method, and others, but these are not the topic of this class. So let's quickly look at Müller's method. This is basically similar to the second method that we saw in chapter 6. So if you remember, in the second method we project a line through 2 points. So we have two initial predictions, for example this and this, and in the second method we use a finite approximation of the derivative. Basically we combine the function values of these two initial values, and the direction of this gives us a root estimate when it crosses the x-axis. And the root is actually this for the black curve, which is the function curve. So Müller's method is similar to that, but instead of a line, this time a parabola is projected through 3 points. So we need 3 points, as you can see, 1, 2, and 3. So, and we have a parabola projecting towards the x-axis, and so the projection of this parabola onto the x-axis gives a root estimate. So this is the basic idea of Müller's method. And in chapter 7.5 we have Bayer-Stokes method. In this this is an iterative approach related to both the Müller and Newton-Raphson methods. So what we do is simply, first we guess a value for the root x equals t. Then we divide the polynomial by the factor x minus t. It comes from here. Then we determine whether there is a remainder term. So this, because actually here it is x minus t equals 0, but here there can be a remainder because this is a numerical approximation now. If there is no remainder, then the guess was perfect and the root is equal to t, because x minus t equals 0 if there is no remainder. Remainder means the other side is not 0. But if there is a remainder, then we need to adjust the guess. We need to change the guess. Then we repeat the procedure until a root is located. So the location of the root means we have no remainder and the root is equal to t. So if this is accomplished, the entire procedure can be repeated for the quotient to locate another root. So this way we can have this Bayer-Stokes method. As I said, there are other methods as well, but these are not the topic of this class. In this slide, we are going to talk about some round of error because of the representation of a polynomial or an equation. So for an nth order equation or polynomial, we have n times n plus 1 divided by 2 multiplications and n additions. So there is n additions and this times multiplications for an nth order polynomial. For example, let's look at an third order polynomial like this with a third order, you can see. So here we will have basically n is the 3 now because nth order, is third order now. And we will use this formulation, 3 times 3 plus 1 divided by 2, 6 multiplications. And we have n additions. You can see 1, 2, 3 additions. And 6 multiplications means here 1 and 2, and here 4 or 3. This gives us 6 multiplication and 3 addition. And instead of having this much multiplication and addition, because each mathematical operation creates a round of error, we want to reduce these operations. Simply we can have a nested format, which means for an nth order polynomial, n multiplications and n additions are required. So for this third order polynomial example, for instance, we will have this kind of representation. So basically here we can just write these in terms of x values by in parentheses having these. This way we will have less or fewer actually operations, n multiplication and addition. You can see that there's one multiplication, one here as well, and one here, 3 multiplications only. This is a similar version, just starting from a0. This is at the beginning, nothing different here. And so computing fx for a given x requires n equals 3 multiplications and n equals 3 additions. So at the top here we have 6 plus 3, 9 operations. Here on the other hand, 3 plus 3, 6 operations. So reducing the number of mathematical operations will reduce the round of error as well. That's why the nested format, this format, will minimize the number of operations, and therefore it also tends to minimize the round of errors. So this is pretty simple actually, if you understood this. And we already gave a homework assignment for this in the and you already did this in the homework, and you will understand what we mean here. And we can have a pseudocode for converting to a nested format. So when we have a polynomial, we simply have this pseudocode, a for loop, as you can see, and we will have this kind of multiplications here, for instance, x plus p and df, and p, x plus aj and p. And p holds the value of the polynomial defined by its coefficients. The a is evaluated at axis. And this p is this p actually, and it holds these. And df holds the first derivative of the polynomial, can be required for some methods like Newton-Raphson. We can, so this is optional. If we use Newton-Raphson, for example, we need to use this to be able to get the derivative. So this is important for round of error. As we said, if we reduce the mathematical operations, we can have reduced round of error. This is an advantage. In the root finding of polynomials, we can have another round of error, and this is because of the an operation called the deflation, polynomial deflation. Let's try to explain this with an example of fifth order polynomial. You can see this is a fifth order polynomial here. We can simply write this in parentheses, as you can see here, and this is a nested form, if you remember from the previous slide. But this nested form doesn't have additional summation or subtraction operations. That's why this is all multiplications. That's why this is also called factored form. So this factored form has the advantage of clearly finding the roots, because we can easily find roots from these. For example, let's say for this fifth order polynomial we have these roots, because when we have this equals 0, all these values will be the roots, actually the negative sign of these. And suppose that in a numerical method we identified one of these, let's say x equals minus 3, for instance. We determine a single root for an nth order polynomial, x equals minus 3, for instance. Then if we continue repeating our root location procedure, we can find the same root, because we will have the same polynomial. We started, for instance, from 3.5 and found x equals minus 3, or the initial guess was closer to this and we found this. Or in in another initial guess, let's say 4.2, we can again come back to this, or let's say 2.5, closer to this, minus 2.5 will again make you reach to this value. So we can find the same root. So instead of, because of this reason actually, to eliminate this finding the same root, if we have a factored form, we can simply eliminate the root from the equation. So we can simply eliminate this term. That's why it would be nice to remove the found root before proceeding. So we just eliminate this x plus 3, remove it by deleting simply, and we will have just the factored form of the remaining 4 terms, as you can see here. And this removal process is called polynomial deflation. Of course, if we exactly found x equals minus 3, there is no issue, we can easily remove, and there is no round of error. But in the numerical methods, the calculated root is not identified exactly. It is identified as an approximation, let's say 3.008 kind of finding of this. And then if we want to eliminate this from the equation, then it will create us a round of error, and it's because of the deflation. So that's why it should be noted that deflation is sensitive to round of errors. And in some cases, round of error can grow to the point that the results can become meaningless. So if because of the deflation, because we will eliminate this, then maybe we found this and eliminated it, and then this eliminated it. So 3 times round of errors consecutively added up, and it will give us meaningless results eventually for this and this, for instance. So we have to be careful about this by knowing that there is such a round of error issue. We have some strategies to minimize the round of error due to deflation, and for that we can have 4 different strategies. The first one is forward deflation. This means that the new polynomial coefficients are ordered in an order of descending powers of x. So from the highest order to the 0 order term, we can order them. In this case, it is preferable to divide by the roots of smallest absolute value first. So this can maybe minimize the round of error. There is also, and this is also called forward deflation, because we are ordering in a descending order. There's also backward deflation. In this, we are ordering in an ascending order of powers, which means from the 0 order to the highest order term. For this case, it is preferable to divide by the roots of the largest absolute value first. So in both, we will have a forward or backward ordering based on the power of the polynomials or variable x, and these two are 2 strategies to minimize the round of error. Another strategy is root polishing, and for that let's consider each successive root estimate obtained during deflation as a good first guess. Each estimate can then be used as a starting guess, and the root determined again with the original non-deflated polynomial. So we will go back to the non-deflated polynomial, and we determine the root again to be able to get the result without round of error. The fourth strategy is comparing each root. So a problem arises when 2 deflated roots are inaccurate enough that they both converge on the same undeflated root. In this case, you might be erroneously led to believe that the polynomial has a multiple root. Recall section 6.5. We talked about the multiple roots. So 2 roots converge to the same undeflated root. But this is wrong because there is actually no multiple roots. But because of the round of error, it happens. So we need to detect this problem. To detect this, we need to compare each polished root with those that were located previously. So polished root means we actually had the root, but it gave the same root actually. Sorry, the polished root is here. The root estimate obtained during deflation as a good first guess. So the first guess, starting guess, gives us the root actually, or the root is the first guess. Then we will use this first guess as the found root, identified root as the first guess, and we will use that to compare with the root located previously. So this study actually discusses this problem in more detail. These can be a little bit more advanced to be able to minimize the round of error, but if you encounter these problems, you can further read these topics from the book as well as from this study.